Hello all, welcome back to my channel Math Made Easy. In the previous session we discussed about reciprocal relations and quotient relations. Just a quick recap. We know that cosecant theta is the ratio of hypotenuse to perpendicular and sin theta is the ratio of perpendicular to hypotenuse. So these are reciprocal to each other. Cosecant theta can be written as 1 by sin theta and sin theta can be written as 1 by cosecant theta. Similarly, secant theta is 1 by cos theta and cos theta is 1 by secant theta. Cot theta is 1 by tan theta and tan theta is equal to 1 by cot theta. Then we have quotient relations. That means when we take any two trigonometric ratios and if we divide it you get another trigonometric ratio, that is the quotient relation. If we divide sin theta by cos theta, you are getting tan theta as our quotient. So tan theta is equal to sin theta by cos theta. Similarly, when you divide cos theta by sin theta, we get cot theta. These are the quotient relations. If you want to know in detail about these relations, you can watch my previous video. I'll provide the link in the description box. Okay, in today's video, we are going to see about the square relations and the trigonometric identities. Okay, our square relations are sin square theta plus cos square theta is equal to 1. And then secant square theta minus tan square theta is 1. Cosecant square theta minus cot square theta is equal to 1. We will see one by one how do we get this. Sin square theta plus cos square theta is equal to 1. Okay, in this figure, take a triangle ABC, right angled at B, and I am taking the reference angle at A as theta. So our AC becomes hypotenuse and the opposite side BC is the perpendicular and adjacent side AB is base. Now sin square theta plus cos square theta. So consider sin square theta plus cos square theta. So from this figure we can write sin theta is equal to perpendicular by hypotenuse, which is BC by AC. So sin square theta will become BC square by AC square plus cos theta is base by hypotenuse, AB by AC. So cos square theta will become AB square by AC square. Since the denominators are same, take the common denominator and add the numerators. BC square plus AB square. Now since this is a right angle triangle, we have Pythagoras theorem which states that hypotenuse square. So in this case our hypotenuse is AC. So AC square is equal to sum of the squares of the other two sides. So other two sides are AB and BC. Their squares are AB square and BC square. Their sum is AB square plus BC square. Right? Now AB square plus BC square is equal to AC square. So we can replace BC square plus AB square with AC square. AC square by AC square, that gives us 1. Hence proved sin square theta plus cos square theta is equal to 1. So we can write now sin square theta plus cos square theta is equal to 1. Then let us say we want to write sin square theta in terms of cos square theta. So we transpose cos square theta, other side becomes sin square theta is equal to 1 minus cos square theta, and cos square theta is equal to 1 minus sin square theta. So we need to memorize these relations. These are very, very important while solving the trigonometric identities proofs. Alright. Next is secant square theta minus tan square theta. Same way, consider secant theta and tan theta from the figure. Secant square theta minus tan square theta. So we know secant theta is the ratio of hypotenuse to base. So hypotenuse is AC. So AC square by BC square minus tan theta is a ratio of perpendicular to base. So it will be perpendicular is BC. Sorry, base is AB. AC square by AB square minus perpendicular is BC square by base is AB square. we have the same base, so we can take AB square common. We get AC square minus BC square. Again we can apply Pythagoras theorem. We have AC square is equal to AB square plus BC square. It implies when we transpose BC square, other side becomes AC square minus BC square is equal to AB square. So we can write as AB square by AB square, which is again 1. So secant square theta minus tan square theta is equal to 1. Hope this is clear. It is just that from the figure you write the relations and then apply the Pythagoras theorem and we get our result. So this is secant square theta minus tan square theta is equal to 1. That means secant square theta is equal to 1 plus tan square theta, and we can write tan square theta is equal to secant square theta minus 1. So as I said, if we remember the first relation, then we can write the other two by transposing the terms. Okay, so we can have the third relation cosecant square theta and cot square theta in the similar manner. I am not showing the proof. So similarly we will just write cosecant square theta minus cot square theta is equal to cosecant square theta minus cot square theta is equal to 1. So if we transpose cot square theta, other side becomes cosecant square theta is equal to 1 plus cot square theta, or cot square theta is equal to cosecant square theta minus 1. This is the third square relation. So sin square theta plus cos square theta is equal to 1, and secant square theta minus tan square theta is equal to 1. Cosecant square theta minus cot square theta is equal to 1. So we need to memorize all these relations. Hope it is clear till now. Then we'll see what do you mean by trigonometric identities. Okay, so basically trigonometric identity means where an equation involving trigonometrical ratios of an angle theta, let us say, is true for all the values of theta, then the equation is called trigonometrical identity. Okay, so each of these relations like are reciprocal relations, quotient relations, and the square relations, all are trigonometrical identities only. Okay, but what do you mean by trigonometrical identity? So before we'll go what is trigonometrical identity, let us understand. So let us recall what is algebraic identity, right? So let us say we have 5a minus 3 is equal to, let us say 3 minus a, right? Now what is the solution for this, or can we call this equation is an algebraic identity? If it is yes, why? If it is no, why not? Right? Okay, let's solve this equation. 5a plus a is 6a, 6a is equal to 6a is basically 1. So if you put a is equal to 1, 5 into 1, 5 minus 3, 2, and 3 minus 1 is 2. 2 is equal to 2. So a is equal to 1 satisfies this. If you put a is equal to 2, then 5 times 2, 10, 10 minus 3 is 7, 3 minus 2, 1, not equal. Right? You take another equation, a plus b whole square is equal to a square plus 2ab plus b square. Right? Now if I put a is equal to 1 and b is equal to 1, right? So 1 plus 1 whole square, 2 square is equal to 1 square plus 2 into 1 into 1 plus b square is 1 square. 2 square is 4, 1 square is 1 plus 2 plus 1 square is 1, which is also equal to, so 4 is equal to 4. So a is equal to and b is equal to satisfies this. If we put, let us say a is equal to 2 and b is equal to some negative 3. A is equal to 2, So it will be 2 minus 3 whole square. 2 minus 3 is minus 1 whole square is 1 is equal to a square. 2 square plus 2 into a is 2, b is minus 3 plus b square is minus 3 whole square. 2 square is 4 plus 2 times 2 4, 4 times minus 3 is negative 12 and minus 3 whole square is 9 plus 9. So 13 minus 2 which is 1. So our LHS is 1, RHS is also equal to 1. If you put some A is equal to 100, so B is equal to some 1000 or 1 lakh, whatever you put. For all the values of A and B, this is true. But is it the same for this equation? It is not, right? So in this case, only A is equal to 1 satisfies. Or if you write the another linear equation in terms of A and B, maybe for certain values of A and B only that satisfies, right? But our A plus B whole square, A minus B whole square, A plus B whole cube, A square minus B square, A plus B whole cube, A minus, all these are identities. That means these relations or these equations are true for any values of A and B. So that's why they are called algebraic identities. Okay, similarly, we have trigonometrical identities. That means now in this case, for example, if we take sine square theta or take some reciprocal relation, we'll take one example from each. If we take secant theta is equal to 1 by cos theta, or cos theta is equal to 1 by secant theta, right? So this should be true for any value of theta. So if I put theta is equal, let us say 45 degrees. Okay, but in order to know this, you should know first the standard angles of trigonometric ratios that we will discuss in the next class. Now I am just showing to you. Cos theta, we know cos 45 is equal to 1 by root 2 and secant 45 is equal to root 2. So cos 45 is 1 by root 2 is equal to 1 by secant 45 is 2. So 1 by root 2 is equal to 1 by, so it is correct. Now tan theta is equal to sin theta by cos theta. Now let us say we will take theta is equal to 30 degrees. We know sin 30 is equal to 1 by 2, cos 30 is equal to root 3 by 2. Then we tan 30 is equal to 1 by root 3. So if we divide sin 30 by cos 30, are you going to get 1 by root 3? So 1 by 2 by root 3 by 2, 2 gets cancelled, we get 1 by root 3. So this is true. So true for any value. Let us take theta is equal to 45 degrees. If we take theta is 45, sin 45 is 1 by root 2, cos 45 is also 1 by root 2 and tan 45 is equal to 1. So if we divide 1 by root 2 by 1 by root 2, we are going to get 1. That means this relation is true for any values of theta. So that's why this is a trigonometric identity. Then we'll see one of these square relations also. Take sin square theta plus cos square theta and take, let us say theta is equal to some 30 degrees. Sin square theta should be sin square 30 plus cos square 30 should give us 1. Sin 30 is 1 by 2. So 1 by 2 whole square is 1 by 4 plus cos 30 is root 3 by 2 whole square. Root 3 by 2 whole square will give us 3 by 4, which will be 1 by 4 by 4, which is 1. Let us take some other angle. Let us take sin 60. Sin 60 and cos 60. Basically we are taking theta is equal to 60 degrees. Sin 60 is root 3 by 2. So root 3 by 2 whole square is 3 by 4 plus cos 60 is 1 by 2, 1 by 4, which is 1. If we take theta is equal to 45 degrees, sin 45 is 1 by root 2, 1 by root 2 whole square is 1 by 2, cos 45 is also 1 by root 2, which gives us 1. So these relations are true for any values of theta. So all these are trigonometric identities only. Hope this is clear. So in the next session we are going to prove some identities using these relations. Thank you.